There's some people there, which is good.
Okay.
They've come back for more.
There's two of us.
Yeah, no, here we are. Thank you, everyone. We've put up some lightning rods in the backyard. Yeah.
Here's one I've got in my hand.
Oh dear, that was awful last night. And then just to boot, I could only get onto my computer with the hotspot, and I didn't have the talk on.
But you have now.
Yeah, we've got all bases covered.
Lessons learned.
Yeah.
We've tried to take on board some lessons as to how we might proceed after that catastrophe.
There's a few people that didn't make it last night. So we're going to actually pick up from where Fred left off yesterday. Alison Fleming says, hi again. That's nice of you. Thank you. And what we'll do is we'll stitch together the two halves of the talk online. So if you did miss some of it, you can go and watch it online, which is why.
Oh yeah. Yeah, so we don't normally wear the same shirts 2 days running, but this is for continuity purposes, because
this is how David Attenborough works.
That's right. Always the same shirt. Manny's going to stitch the two halves together and make it into one talk. Actually, what I'm going to do is pick it up a little bit before we lost it, just to remind you of what was going on, and hopefully that will mean that everybody understands it all. Richard is asking for his money back.
Someone says, why put up a lightning rod? Lightning doesn't strike twice.
Oh, there you go. That's right.
Yeah.
Well, maybe not. I do have a colleague in the UK, an astronomer, who was struck by lightning. Unusually, he was in a submarine at the time, but he was on the surface. He was struck by lightning, but he was also in a major plane crash, and he survived both. So maybe these things do strike twice.
We don't want to try it.
No, we don't want to try it. So keep away from submarines.
And Judy, yes, it was Mandy's fault. Yeah, absolutely. We'll blame him. We've got people from Western Australia, from the UK. I think we've got someone there from America. So it's lovely. It's really nice. So it's an online family now.
It is, whether you like it or not.
Oh, and Tassie, yes, John, yes, you're in Tassie too. Ready for round two. So, here comes Mandu. We heard his name. Yes, okay, we'll show you. Here we go. Yeah.
Oh dear, if I get him to give the talk.
Good evening, everyone.
Oh, there he is.
Yeah.
Oh, pussycat.
He's been asleep on the couch most of the day in this cold Sydney weather.
Yes.
Yeah.
Certainly.
I don't know what the rest of the country's doing. Oh, put you back down there.
Tony's from Bradford. That's champion, a grand place to come from.
Originally from Bradford, but not there now.
Not
yeah.
there, no.
Yeah, Mandy's got the same outfit on too. Oh dear.
I think we should abandon this and just let everybody
leave
else.
You open to comedy.
It's great.
This is online comedy.
Yeah. So how are we doing for time?
I don't know. We will kick it off in a second or two.
It must be somewhere.
And then I'm sure you've got lots of great questions because you had 2 days to think about it.
I've got one in my head that I'm carrying over from last night as well that I saw come up on the screen. So we might just give that a brief airing. And
just a reminder, if you do have questions, it's easier if they go in the Q&A box down the bottom, just there, wherever you're placed on your screen. So, Fred, I think from rural Balangara, where's that near, Lynn? It's exercise in geography as well.
Yeah, it's good. So I like the idea of Mandu being called lightning.
John, that's not very nice.
John Latanzio asks why I'm getting uglier. And he commented on that yesterday as well, so it's happening quite rapidly. I think it's to do with COVID-19. Yes, Mandu, that's right.
Oh, yeah.
30 kilometres northwest of Port Macquarie.
Ah, all right.
That
There we
sounds
go.
lovely.
Well, Mandu, don't lick my face. All right. I think, Fred, you should get going.
Let's do it.
Who's doing your makeup, Fred?
Thanks
Mandu.
for that. Yes, quite.
They did say that was one of the funniest things on television. All these reporters coming on television who have done their own hair and makeup, and it's not quite as professional as it used to be.
I did my own hair today as well, actually. So yes, very good. All right,
Okay.
7:33. You mentioned neutron stars yesterday. Where have the protons and electrons gone, John? Thank you very much. That's the question I just mentioned a minute ago that I saw go past last night, and I will get to that when we've wrapped up the talk, which hopefully won't take all that long, but we'll get going.
Get going.
Get going now. All right.
Yep.
Look after that.
I'll leave you. You leave me and Mandu.
Yeah, here we go.
If anyone wants to, Mandu has a Twitter handle, which is at Mandu1922 or something. I can't remember. Anyway, I'll look it up. And yes, he likes to have people send photos of their cats too. All right, Fred, are you sharing your talk?
I'm sharing the screen.
Excellent.
As we speak.
And Mandu and I'll say goodbye.
So, Marnie, can you see Exploring the Transient Universe?
Yes.
Get this lightning rod out of my pocket, sorry. Right, okay, that's good. So, just to recap briefly, yesterday, a lot of the talk was basically an introduction to what's happening in Australian astronomy, and I talked about our relationship with the European Southern Observatory, the fact that Australian astronomers have access now to the 4 8.2 metre telescopes of the very large telescope, but also about the Square Kilometre Array and its precursors, because they are very important to the story that is now about to unfold. So I'm going to pick it up where we introduced the idea of fast radio bursts. So the first few slides will be a repeat of what we said yesterday. I'll go through them very quickly, but I just wanted to set the context of where we got to. So fast radio bursts, as I mentioned, the story started in Parkes with Duncan Lorimer going through archival data from the Parkes dish, looking for pulsars, which are essentially neutron stars spinning rapidly and flashing this lighthouse beam of radiation, which we see as repeated pulses. That's not what he found. What he found was something else, which is this, the Lorimer burst, at that burst of radio frequency radiation, which has that characteristic slope to it when you plot the frequency of the signal against the time in which it comes in. This was a millisecond wide, but it has the characteristic slope that tells you it's come a long way through intergalactic space. It's traversed the electron fields of that space beyond our own galaxy. So that was what really got people interested. And then, of course, I had to tell you about the periton story. That was a periton, the mythological creature, which was, when the signals were analysed, they were certainly linked to the rotation of the Earth, not to mention the fact that they always seem to turn up at lunchtime. And it was, of course, the microwave in the Parkes lunchroom, and that story of the two Johns, John Sarkissian and John Reynolds, actually analysing what was going on. It's when you press the door open button before it's finished, that sends out a periton. But Arecibo had detected more of these things, and in particular in 2015 they found the first repeating fast radio burst, which is called, and I couldn't tell you this yesterday because my face was in the way. You've got to come out of the presentation to move your face. That's the secret. 12/11/02, that was observed on the 2nd of November 2012. It's the way these things are written down. And that's a repeating fast radio burst, which, of course, as I said, ruled out a single cataclysmic event. And we had a look at this, which shows whereabouts in the sky that burst seems to come from, the outskirts of a fairly anonymous dwarf galaxy, but one that is a long way off, 3 billion light years away, not on our doorstep by any means. This is the slide I got to when we had the lightning strike, if that's what it was. Something actually devastated our phone line because the phone rang at the same time as we lost the internet. It all comes in the same cable. This is where we got to. And I think I just mentioned a new era of fast radio burst research. And the fact that ASCAP, the Australian Square Kilometre Array Pathfinder, those 36 dishes, have the detectors at their focus or their foci, which allow you to essentially build up an image with each one of those antennas, and that's what the artist's impression is showing you there. Essentially something like the pixels of an image sensor, which is effectively what this is, but in the radio region of the spectrum. And also, and this is where the talk came to an end, I was mentioning that what you can do with the 36 antennas is use them all, but rather than using them as an array in which they're all pointing at the same object, and the reason why you do that is to mimic a much bigger telescope, one whose size is effectively the whole size of the whole array. What you do, instead of pointing all of them at the same object, is you offset them slightly. To mimic a fly's eye, and as you can see there, it's called fly's eye mode. So you're just moving each telescope slightly away from what the next one's pointing at and building up a much bigger image of the sky, 1,000 times the area of the full moon. And during its first year, which started, I think, towards the end of 2017, it found 20 of these, just serendipitously, pointing this fly's eye mode telescope into space in what looks like likely regions. And I suspect that what they did was concentrated on the part of the night sky, excuse me, which is away from the Milky Way, because that is where you see the information coming from distant galaxies. The Milky Way itself blocks off our view of the wider universe, but if you point away from it, actually towards what we call the North and South galactic poles, in our case it's the South galactic pole, that would be the kind of region, I think, where they would have been looking for these things, knowing already that the Lorimer burst had come over a great distance. So what happened? Well, they found some. And what they also found is that they're all over the sky, as I said, predominantly away from the Milky Way, but not just clustered in one area of the sky. And if they're a long way off and they're all over the sky, that means that they are very common. And very quickly, people started estimating how many of these things might be going off that we're not seeing. And I saw numbers like 10,000 a day that they're popping off all over the sky. And we are really only just learning about them. You know, it's only a few years that we've actually been talking about fast radio bursts, these very transient phenomena. And that's where this link with the New Deal with the European Southern Observatory became important, because the ASCAP ones were followed up, as it says, by Australian astronomers using the very large telescope up there on Cerro Paranal in northern Chile. And in fact, there was one in particular which had an early paper written on it, FRB 171020. I think that was one of the first ones detected by ASCAP, 20th of October 2017. And that was essentially because ASCAP can measure its position very precisely, being a wide field telescope, that means that you can then point an optical telescope, a visible light telescope like the VLT, directly at it. And that is when that was confirmed. What it says there, the FRB was found, or the event was found to come from the outskirts of a normal galaxy 120 million light years away. So, excuse me, significantly nearer than the repeater that we mentioned a minute ago. That team, led by Keith Bannister et al., have been following up more recent discoveries, but the search is now very competitive, as you'll see in a moment. Let me, before I do that, though, put up a picture of my great hero in this science. One member of that team is Stuart Ryder, excuse me, formerly of the Australian Astronomical Observatory, so a colleague of mine, now part of an organisation called Astronomy Australia Limited, which actually has a lot to do with these facilities overseas, as well as Stuart being an astronomer in his own right, winning his own time. He had a great trip. He might even have had more than one on Sophia, the airborne infrared observatory operated by NASA, which often flies out of Christchurch down in New Zealand, and actually Stuart is a Kiwi. But Stuart's my inside informer or informant on all things to do with the fast radio burst mystery, including some things that I'm not allowed to talk about, but it's all right because my memory's so bad. It's very hazy anyway. But the work is ongoing. There's a lot happening. So what is the competition? Well, here's one of them. This is a radio telescope in British Columbia. It is called, and I mentioned it, I think, in the question time last night, the Canadian Hydrogen Intensity Mapping Experiment, which looks a lot different from ASCAP, as you can tell. In fact, it's more resembling the Murchison Wide Field Array, which you remember is electronically steered. This does have a sort of parabolic cross-section to it, but it is really a very wide field telescope, and it's turning up FRBs in large numbers because it looks at a much wider area of the sky, including some new repeaters. 20 is the number that I heard probably 2 months ago or so. I haven't had an update on that, but they are certainly, they've found, you know, more than one. I think the last publication I saw had 8 repeaters in it, but I think there are more on top of that since then. As I've said there, the telescope, whilst it's great at looking at the whole sky and pulling in fast radio bursts, it doesn't have particularly good directional sensitivity. You can kind of get a rough idea where in the sky you're seeing these things, but it's not like ASCAP. It's not pinpointing the direction to your source. And so what that means is that trying to find out where these things come from is not easy unless you're lucky and you get it in the field of view of another telescope, or you're looking at a repeater. The great thing about the repeaters is they're always in the same place. And so if you know that there are some that repeat, then you can follow them up with other telescopes. And one of them, that is exactly what happened. FRB 180916, the 16th of September 2018, was a chime detection, a repeater. And the fact that it repeats means you can home in on where it is. And it was followed up by Gemini North, one of the 2 8-meter Gemini telescopes, one in Hawaii, one in northern Chile. And so one of those telescopes followed it up. The image that you see there comes from Gemini, and the green circle is where the fast radio burst was located. That burst came from a really nondescript region of this really very normal spiral galaxy, 500 million light years away. That paper came out, or the announcement was made at the beginning of the year. And that's, you know, in a sense, it's building up a pattern here. Even though we've only got a handful of these localizations, they do seem to be not from the centers of galaxies. I think I mentioned that in the question time last night. Not from the place where you would expect to find the most activity. You know, there's a black hole, we think, in the center of all these galaxies, a supermassive one, millions or billions of times the mass of the sun. And you'd expect in a high gravitational environment like that you might find something that is making these fast radio bursts. But the ones that we're finding are not in places like that. They are on the outskirts. Now, this particular one actually turned out to be even more interesting. As I said, on the 13th of February, it hit the headlines again with this paper that for the first time identified a periodic behavior. So all the repeating fast radio bursts seem to, you know, they do repeat, but it's completely random. They'll go off one day, maybe the next day, then 2 months later. It's a random process, as we might call it, a stochastic process, to give it a kind of fancy name. But 180916 has been found to have a period, not so much a period as a pattern. And the pattern is really amazing that, you know, you can find this sort of thing. What you do is you put the bursts through an analysis program. So as you might be able to read in the abstract from the paper, which was written by the Chime FRB collaboration, there is 16.35 day periodicity. So this pattern repeats every 16.35 days. And what you get is a 4-day window within that period, and I think it's always the same 4-day window at the beginning or the end, in which there are bursts. Sometimes you don't see any bursts, sometimes you see multiple bursts within that window, but it's always the same pattern, that there's this 4-day window within the 16.35 day period. This is based on an analysis of, I think it says there somewhere in the in that article, it's about 20 or 30 bursts that were observed. So the bottom line of that abstract is our results suggest a mechanism for periodic modulation, either of the burst emission itself, in other words, whatever is causing these bursts, that is somehow being blanked off, is somehow switching on and off, and then they say, or through external amplification or absorption. Now, I think by amplification, they probably mean something like gravitational lensing, which would suggest that it's next door to something with a very intense gravitational field, or absorption, and that might be something blocking off these radio bursts. You know, the suggestion is something like a magnetar, and we'll be using that word a lot over the next 4 or 5 minutes, which is a very, very highly magnetic neutron star. And you might remember, I started off the talk yesterday with an artist's impression of what a magnetar looks like with all its magnetic field lines. I've got another one coming up in a minute. But if you imagine this highly magnetic neutron star, and a magnetar is at least 1,000 times more magnetic than a standard neutron star, which in itself is gazillions of times more magnetic than the Earth is. So that, if you imagine a magnetar which is somehow causing these fast radio bursts, but is perhaps in orbit around something else with this 16.35 day period, then you might get periods where these things are blocked off, or certainly not visible to us. There is something clearly going on. So that is a really important piece of research that was announced, as I mentioned, in February. But it gets better, because last month, and it is still last month because it's the 30th of April today, there was another breakthrough which came once again from this combination of ASCAP detecting the fast radio burst and follow-up from the European Southern Observatory. And this is a burst that doesn't repeat. This is a single shot radio burst. Its name is 181112, as you can see, 12th of November 2018, when it was first observed. But what this highlights, and I'm delighted to be able to say this, it highlights what a fantastic piece of equipment for discovering things like this ASCAP is, because ASCAP is perfectly honed to find the details of a big mystery like this. And the paper title, which looks probably like gobbledygook, but it kind of tells you that. So it is entitled Spectropolarimetric Analysis. What that means is that ASCAP is looking not just at the intensity of the different frequencies of radiation that it's looking at, it's also looking at the polarization. I'm sure most people are familiar with polarization in the visible light region of the spectrum, because most of us have at least had or have got polarizing sunglasses, which essentially inhibit the reflections coming off the road when you're driving. They're great for driving. What polarization is, if you think of a light wave or a radio wave doing this, polarization is the angle at which that wave is being made. So horizontal polarization would look like that. Vertical polarization looks like that. And that's why your TV antennas, because most of the TV signals the higher frequency ones were horizontally polarized. It's why your TV antennas were, you know, had these this kind of flat appearance with all the spiky bits sticking out. Well, I'm sure radio astronomy engineers and scientists are you know, they're cringing at my description of what is technically called a Yagi aerial, but that's how they work. So the ASCAP can actually detect the polarization of the radio signals, and that's important in understanding the medium through which the radio signals have traveled. We find the same in visible light astronomy. If you, and there is a group at the University of New South Wales, led by Jeremy Bailey, who've built this, an optical polarimeter with part per million sensitivity. It's an astonishing piece of kit. It rejoices in the name of Hippie. And one of the things that you can use Hippie for is to look at the light that's traveled through dust, because dust in space actually affects the polarization of the light. So it's a great way of detecting dust. Jeremy's goal with Hippie, though, is to measure the polarization in rainbows on extrasolar planets. That's something not to do with this talk, but it gives you an idea of the fact that polarimetry is a very, very powerful technique, and they can do it with ASCAP. But the other thing that they can do is on the next line, microsecond resolution. So we've already talked about the fact that these fast radio bursts come with basically a length of a millisecond or thereabouts. But ASCAP can break that down 1,000-fold. So you can look at any details that there might be in those bursts. And indeed, the details are there. Let me show you just one of the diagrams from this paper, which looks complicated, but we only need to concentrate on one thing in it. And that is in the upper left, there is a diagram which is called A, as it says in the upper left corner. What you're seeing there is actually, that's the intensity of the different polarizations that you're looking at. But don't worry about that. You can see there I, Q, U, and V. We don't need to worry about that. Just look at the spike on the left there. You can think of that as the intensity of the burst. But look now down at the bottom, because what you've got there is a 1.5 millisecond timescale. And you can see that ASCAP is able to break that down into, well, as we said, microsecond detail, microsecond observations. And what you see there is not just one spike, but there's another one as well, which you can see at a time of 1 millisecond after 0. And there are actually two more. The vertical dotted lines are actually where the pulses are. So there have been 4 separate pulses in that, what might have been thought of as a single fast radio burst. It's broken down into 4 separate pulses, and that's really important and gives enormous clues. And I'll explain why in a minute, but let me just go to the end of this abstract, because in what they say is that it demonstrates that their method, which facilitates high time resolution polarimetric observations of FRBs, can be used to study not only burst emission processes, in other words, what it is that's causing the burst, but also the diversity of propagation effects present on the gigaparsec path they traverse. A gigaparsec is about 3 billion light years, okay? A bit more, 3.23, I think, billion light years. Parsecs are a different unit that astronomers use, but they're related to light years. So what that sentence says is that you can analyze what is causing the bursts in great detail, but you can also look at the material it's come through, just as I explained. And there's a very nice diagram or an artist's impression which shows this happening. Up on the left there is FRB 181112, the host galaxy with this object in it. And that pulse of radio waves has come down to Earth. Now, 2 things to point out. There is a nearby galaxy that is near the path that radio wave, that radio signal has come, because you can see that on the ESO imagery. But the pulse of radio waves you might have thought would have been affected by the cloud of plasma around that intervening galaxy. But it turns out that it wasn't. It's actually, the scientists have been able to use that pulse to give you a kind of an upper limit on what kind of polarization there is from the intervening galaxy. So that's a great result. What it's telling you is that potentially these fast radio bursts give you a way to probe the intergalactic medium, to probe the material between the galaxies. And that is probably going to be one of the next big things in this science. But the other thing about it, yes, we've got a pulse there. Let me just go back to the diagram. So that pulse is, you know, something like 10-ish, no, probably 50, 100 microseconds wide. And it's analyzed at the microsecond level. That profile is not just not just an approximate profile. That is what is actually happening. That's the profile of the signal. And very short bursts of stuff from anything tell you something about the nature of where they're coming from. Look again at the galaxy at the top there. If you've got something, say you've got a pulse that is 10, let's say it's 10 microseconds wide, that tells you that it cannot have come from an object that is bigger than about 3 kilometers. And that's because 10 microseconds is how long it takes light to travel 3 kilometers. And if you've got something bigger than that, the pulse is spread out. It's a much broader pulse. So what that work is telling you, and this is the great strength of ASCAP, is that yes, these signals are coming from something very small indeed, something very compact. So that kind of narrows down the field a bit. A little incidental comment here, and I really only put this in because I think this is a lovely picture of one of the 4x4, not 16 by 16, as I said yesterday, 4x4 tiles of the Murchison Wide Field Array. It's a lovely shot, but they don't see the FRBs. And that's because, as it says, they have too low a frequency response. So, and the background to this slide gives you the clue. This is an artist's impression of a magnetar in a cluster, a star cluster called Vesterlund 1, which has been actually analysed by ESO scientists. I'm just using that as a backdrop, which probably gives you a hint as to what's coming. What are FRBs? Well, we still really don't know. And this, what I've put there is probably what 3 months or so ago were the two best guesses. Flares on these highly magnetic neutron stars, or perhaps neutron stars themselves colliding. And that's still a possibility. That has not been ruled out yet by the work that's going on. And you can kind of imagine that if we could, using LIGO, the Laser Interferometric Gravitational Wave Observatory, and the other gravitational wave observatories that have now come on stream on Earth, if we could use those to detect two colliding neutron stars, that's been done already, but also pick up an FRB from it, that might actually reveal that, yes, perhaps it is colliding neutron stars. But I have to say, flares on magnetars, I think where this is going at the moment. It's certainly seems to be the most popular idea, as you'll see in a minute. What we're doing is all going to help to try and analyze and try and identify this. So as I've said there, identifying the host galaxies to look for common properties will help. And we've found one common property so far. They're all in, the kind of standard regions on the outskirts of galaxies. There's not really anything special about where they are. That periodicity, the FRB 1809-16 that I mentioned before with its 16.35 day period, could be a breakthrough because it might tell us that, yes, perhaps this is coming from two objects in orbit around one another or something like that. As does what we've just been talking about, these microsecond subpulses from 1811-12. They are also telling you something, namely that these sources are very, very compact. And there's this sort of echo as well. There's the fact that you don't just get one burst, you get, like there were 4 bursts in that, in 1811-12 there. Something happening, something about the, maybe the environment in which this is taking place that is causing that, that fine structure, you might call it, in the radio bursts. But there's more, and this is what I was going to tell you about yesterday, because this news only came in yesterday. And once again, thanks very much to Stuart Ryder for pointing this out to me. So the stop press, this is, you might be able to see the date on that astronomy telegram, which was actually the day before yesterday, but there's something that happened yesterday which sort of is related to the same story. And the article is headed "A Bright Millisecond Timescale Radio Burst, aka a fast radio burst, from the direction of the galactic magnetar SGR 1935 plus 2154. Now, on the right is a picture of a magnetar in our galaxy, one of these highly magnetic neutron stars. It is part of our own galaxy, so its distance is measured in thousands of light years rather than millions or billions of light years. What you're seeing there is a cloud of dust around this object. You can't see the object itself. It's actually in the dead center of the image, so that bright blob that you can see near the middle is actually a cluster of bright stars. This is an image made in the infrared, so they are sort of infrared false colors. But magnetar is the remnant of a star that has gone through a supernova. When a star turns into a supernova, all kinds of things happen in its environment, and you can see that there is this dusty environment around that particular magnetar. However, so that's not the one that's being talked about here. I just put that there to give you an idea that these things are relatively nearby. They're not at galactic distances. So this has come from a CHIME, and the CHIME consortium, the CHIME FRB consortium have identified what you could call an FRB, but it's come from something in our own galaxy, and it's something that you can actually identify with a magnetar. The other astronomer's telegram that came out the following day, that was yesterday, is an independent detection of that same burst, but with a different telescope. And essentially, what these people, and I think they're based at, yes, they're based at Caltech and JPL, so it's a sort of California group. They are saying that maybe what we're seeing here is an instance in our own galaxy of what these fast radio bursts are in other galaxies. It's still, I think, a very preliminary work. Stuart, when we spoke yesterday, I think was a bit skeptical about it, but he thinks whilst the conclusion, which I'll read out to you in a minute, is probably correct, or probably has truth in it, it might not be the whole story. And that's the way science works. You've got to be aware that it might not be the whole story. So what they say at the end of this, you might not be able to read it, it says, "We conclude that active magnetars," and by that it means ones that have got X-ray flares on them, because this particular one is very active in the X-ray region of the spectrum. There's all sorts of things happening. So we conclude that active magnetars are a source of FRBs at extragalactic distances. We encourage follow-up observations. There you are. That's what all good scientists do, get working on it, because this might be the big breakthrough that we've needed on fast radio bursts. If they can all be proven to be at to have a magnetar, a highly magnetic neutron star related to them. There's one scientist who is very eminent indeed, who thinks he already knows what they are. This is Avi Loeb, who's the director of the Harvard Smithsonian Center for Astrophysics. He thinks they might come from extragalactic light sails, which are things being blown along by lasers from extragalactic intelligences. So I should explain that Avi is always a bit provocative when it comes to explaining things. And, you need people who think outside the box, and he certainly does. The idea that fast radio bursts might be extragalactic civilizations beaming their light sails along is interesting. And let me just read the first couple of sentences of the abstract, because it's worded very carefully. We examine the possibility that fast radio bursts originate from the activity of extragalactic civilizations Our analysis shows that beams used for powering large light sails could yield parameters that are consistent with FRBs. There you are. That's the way to put it when you're saying we don't really know, but it could be. So by that, he means that the physics holds up. I don't think anybody believes that. I don't believe Avi believes it either, but he's put that forward as a, as a suggestion. And it's not without some sort of sense, because we are already using light sails. In fact, we use, yes, sometimes called solar sails, but light sails to propel spacecraft. There is one that had a bit of a breakthrough last year. I think it was just called Light Sail 2. I believe it was the project of the Interplanetary Society. I should have checked this. I did talk about it on the radio. This is a light sail, not the one you're looking at there, but it's something like that. It was deployed in Earth orbit, and they demonstrated that the radiation of the sun actually accelerates the spacecraft. So its orbit was modified by the radiation of the sun. Now, that's not quite the same as blasting yourself along as an intergalactic traveler, but it demonstrates that the thing will work. What's Breakthrough Starshot? It is a project funded by Yuri Milner, who's a Russian billionaire who set up a number of what he calls the breakthrough projects. Breakthrough Listen is something that occupies two of the world's great radio telescopes, one of them at Parkes, basically listening for signs of signals from extraterrestrial intelligence. But Breakthrough Starshot is basically it's a feasibility study. It's looking at the possibility that you could use a light sail like the one you see there, with a little spacecraft at its center, and then blasted along by lasers, which don't yet exist because they're so powerful, to send it to the nearest star, Proxima Centauri, which is known to have a planet that may be Earth-like. It's still actually a fairly controversial observation, but it's the nearest star, 4.3 light years away. The problem with that distance is that if you're using conventional rockets to get there, it takes you about 60,000 years, and everybody loses interest in that time. I certainly would. But if you could use a light sail, then you're not relying on chemical fuels. You're relying on these gutsy lasers that you've put into Earth orbit, and you blast the thing along. And if you can accelerate it to, a third of the speed of light, to 100,000 kilometers per second, over a period of time, then you've got the wherewithal of making the journey, rather than making it in 60,000 years, making it, in something like 20 years, that kind of time. So you have your spacecraft whizzing by Proxima Centauri's planet. If you can control it to that level, it takes its pictures and all the rest of it, and then sends a signal back, and it takes 4.3 years to get here. It's a long process. So this is not by any means a proposal to do this yet, but it is a feasibility study. I'm not quite sure how they're doing. One thing that is of interest is that Avi Loeb, who we were just talking about a minute ago, actually sits on the board of Project Starshot. And before you get excited about the idea of spacecraft taking people or animals or whatever to the nearest star, the kind of size scale they're thinking about for these spacecraft is like this. This is one of the printed circuit boards that occupies the most of the spacecraft that you have the light sail operating with. So it's technology that is not yet really in any sense practical, but maybe one day it will be. And so maybe, just maybe, there could be civilizations out there that are using light sails to bowl around the extragalactic universe. To be honest, I think it's very unlikely. They'd have to be everywhere, because we see these fast radio bursts all over the sky. And to my mind, there's still a mystery. I think a natural explanation, like perhaps flares on magnetars, is a much better one. And ladies and gentlemen, that is the end of the talk. We made it this time. So the story has a moral. The moral is further observations are encouraged. Watch this space, because we might have new discoveries coming out within the next few months. I think there's some very exciting work that we're on the brink of seeing. That's one of the morals of the story. The other is watch out for those pesky microwave ovens And I love the oven roasted periton that there is sitting in that one. Thank you very much again, everybody. We made it to the end without a disaster, and I'm delighted that you were able to join us once again. And of course, Marnie will now moderate any questions that you might have. Thanks again.
Thank you, Fred. Yay, well done.
Oh, pleasure. It's not just me.
Get hit by lightning or anything.
No, not yet. No, the lightning conductor, you see.
So I have a few questions come in and probably related to the microwave. Mrs. Trellis from Netherwallop, Hampshire, not to be confused with Overwallop, wants to know what happens if her radio bursts. She's worried she won't be able to hear the archers.
Well, that's right. There's about 7 in-jokes there, I think. But I do like the idea of a fast radio burst. When your radio's sitting there 1 minute broadcasting and next minute it's gone. It's a bit like what happened to us last night. So thank you, Mrs. Trellis. That was very much appreciated.
On a more serious note,
good.
So have you mentioned, sorry, I was a bit distracted with Mandu during the evening. Did you answer John's question about neutron stars? And
no, let's start with that one. So it's a really interesting question, and neutron stars, as it turns out, are not just neutrons. Something like 10% of them are protons, and of course protons are electrically charged, and another 10% are electrons, which are also electrically charged, and they cancel each other out. But so the neutrons haven't the protons haven't disappeared. They are there. I'm not sure of the mechanisms that lead a neutron star to be more made of neutrons than the protons. I'm sure it's something to do with the collapse when it goes supernova, because all kinds of weird and wonderful energetic processes take place when that happens. But it does answer one question that, John, you might also have had in your mind, which is how can something that's just made of neutrons with no electrical charge, how can it generate these incredible magnetic fields? And the answer is that apparently the protons are themselves in the outer layer of the neutron star. There's a fair bit of stuff on the web if you care to have a look at it. The outer layer, and that's where the magnetic fields are generated. So there are clearly things that we don't understand about these things, like magnetars themselves, which are even more magnetized. But it is all about the layer of protons on the outside. Really interesting stuff, far beyond the astrophysics that I learned 100 years ago, but it's all there, as I said, on the World Wide Web. So have a look. It's a great question, and thank you very much for asking it yesterday.
Greg Nielsen has not asked a question, but has very kindly said, and the crowd goes wild with applause, which I thought was sweet.
Thank you, just because we made it.
Yes. Yeah, maybe. Oh, thank God it's over.
Yeah, exactly.
So John Bijowski says, do all galaxies have black holes, and why do we call them black? Yeah,
so we think they do. We think that all galaxies do have supermassive black holes at their center, millions or billions of times the mass of the sun. And the reason why we call a black hole black, it comes about, it wasn't actually John Wheeler who coined the phrase, but he was the one who brought it into popular use in 1967, I think. A black hole is... Until then, they were called something like spherically symmetrical relativistic gravitating objects. So black hole's a lot easier to say, but it's defined as a point, a single point with no dimensions, where the density is infinite. The density of space has become infinite. That's the definition of a black hole. And if you've got an entity like that, and as I mentioned last night, if people were listening, people might have hopped off by then because we'd had the accident or the lightning strike. But I mentioned that the work that Jocelyn Bell Burnell did actually went a long way towards convincing people that black holes could be real physical entities, and we now know that they are. The main property of one of these things, because its gravitational pull is so intense, and it's got a huge gravitational, what you might call the slope of the gravitational field, that is itself very highly curved, so light can't escape from it, and that is why they're called black holes. And it's the event horizon, is that sphere, imaginary sphere around a black hole, which is the kind of point of no return. That's the point which light can't get past. And that would look black if you could see one. We've already seen the silhouette of one of these with the Event Horizon Telescope observations that were released early last year. But the Event Horizon itself is thought to be black, and is black because that's where light can't travel, hence the name. Thanks for the question.
Excellent. And John would like to know, are there magnetars in our own galaxy?
There are, and that last picture I showed you of the one in Vesterlund 1, the cluster of stars, that is in our own galaxy. I'm sorry I don't have its distance off the top of my head, but it is, I think, its distance will be measured in thousands or perhaps tens of thousands of light years, not millions or billions of light years like the extragalactic ones are. So yes, there are magnetars in our galaxy, and not just one. There are, I think, quite a number of them.
Okay, and then following on from that, Graham wants to know, is a magnetar just a highly magnetic neutron star, or is it more to it than that?
My understanding is that it's exactly what it is. It's a much more extreme version of a neutron star with, as I mentioned, more than 1,000 times more magnetism. That must, have some cause in terms of its structure. I don't know what that is, but they are seen as a more extreme example of what a neutron star is like.
Okay, so this is triggering questions. If it does not affect the burst travelling towards us, asks Fotini, how can we determine anything about the intervening galaxy?
Yes. So that's the point that I was trying to make. If you've got the burst coming towards us, let's go back to that, because that's a really I think that's a really nice graphic of what's happening there. Can you see that, Marnie? Is that coming up?
Yep, got it. Mm-hmm.
Yeah. So the medium between the galaxies is, you might think it would be empty, but it basically has high, there are clouds of gas in there, as well as the dark matter, which we know inhabits the universe. And we expect that those pulses of radio waves will be affected by that. And if you have a galaxy that is close to the line of sight, exactly as is depicted there, you would expect that as the pulse of radio waves goes through its outskirts, that it might be, the polarization might be affected. But with this particular example, I think I'm right in saying this, I only read the abstract of the paper, but I think I'm right in saying that it didn't have the effect that was expected. Even though it was expected that the pulse was going to go through the sort of outer reaches of the gas cloud in which that galaxy is embedded. It didn't have the effect that was expected. And what that does is sets an upper limit for the gas density out there. So even though you didn't see the polarization changing, it does tell you something about the gas around that galaxy. My guess is that we will hear much, much more about this kind of thing before very long. And we might even be able, be using these to essentially probe the gas clouds in which galaxies are embedded, if we can learn to detect them and, analyze them properly and perhaps understand them better than we do. So a great question. I'm sorry, I probably didn't make it clear the first time through.
Okay, and then Ethan wants to know, how do they become so energetic?
Yeah, that's once again, I think still a bit of a puzzle, because it's a bit like if you think of a standard pulsar, a neutron star that's rotating and fanning out this lighthouse beam of radiation, if you accept that here on Earth, we see that beam pulsing out, what that's telling you, once you know what it's coming from, that it is a neutron star, is that this thing is not radiating the same amount of energy out to the whole universe. It's beaming it in our particular direction. So in some ways it looks brighter than it would if you were off the beam, you probably wouldn't see it at all. And so that begs the question with these fast radio bursts, are we seeing a phenomenon that depends on us being in exactly the right line of sight? Is it some sort of beamed radiation, or is it a star like a magnetar with a flare on its surface, which is the current, as you can see, the current best guess about these things? Is that beaming radiation throughout the whole universe, isotropically, which means all the same in all directions? Or is it beaming it in a preferred direction and we happen to be seeing that? We don't know the answer to that. That clearly has a great influence on what the amount of energy that's being released is. Because if it's going throughout, if it's isotropic, if it's going everywhere, then that is much more energetic than if something is actually beaming its radiation towards you. So I think the jury is still out on exactly what energy sources these have, except to say, just to add, that we know about these flares on magnetars because we see them in the X-ray region of the spectrum. There are several spacecraft, Chandra is the best known one, which have been built to look at X-rays. X-rays don't penetrate the Earth's atmosphere. It's a bit comical because they penetrate everything else, but they don't come down through the Earth's atmosphere, mainly because they're very faint, the cosmic X-rays. And so we see these flares in X-ray, and I'm sure people have got some idea of how much energy they generate from those observations. That has to be reconciled with what we see from the FRB observations, if they are the same thing, but they might not be. We simply don't know. I don't know.
We've been nothing. I think I'm understanding that you may have just answered this question from Jim, but maybe you could verify that. Fred, FRBs towards outskirts of visual galaxies, but where are they placed? Image of the galaxy concerned. Sorry. And then, he goes on to say, and those in our galaxy, are they located on the outskirts of it?
So, look at this picture. Can you see that, Marnie? Is that correct?
Yeah, got it. Mm-hmm.
Which is FRB 1809-16. You could sort of say, okay, maybe that galaxy just happens to be in the way, and what we're seeing is something in front of or behind the galaxy. But the evidence so far, and there are only small numbers, but the evidence so far seems to be that this is typically the place where you do find these fast radio bursts coming from. And so that is a real, it's a real juxtaposition. The other thing that helps you rule out the galaxy and the fast radio burst being at different distances is that you can actually measure the distance. Once you find a galaxy like this that seems to be associated with a fast radio burst, you can measure the distance of the galaxy. We measure what's called its redshift, and that gives us the distance. And so far, all the ones that have been observed, that distance has been basically compatible with the dispersion measure that you get for the fast radio burst, because we get a crude measurement of the distance of the fast radio burst by that sloping line of radiation that I showed you in the Lorimer burst. So these two are two independent measures of distance, and if they turn out to be the same, or at least compatible with one another, then you can be pretty optimistic that what you're seeing is a real phenomenon, that the fast radio burst is actually within the outskirts of the galaxy itself. Hope that answers the question, Jim. And
our final question from Jared. He asks, Fred, does the observation of an FRB vary depending on where the Earth is around the sun?
Yes, in terms of the, just the physical process of making the observation, but I don't think there is any systematic, you know, I don't think we see more at certain seasons of the year, for example. And that sort of, it's a little bit related to the periton issue. It was the fact that these things were all turning up at this relatively the same time of day that led to the understanding that this is something to do with the Earth, and indeed something to do with the park's lunchroom. By the way, there were 2 microwaves at parks. One of the little secrets that John Sarkisian let me into, which I probably shouldn't have said, but never mind. You know, the fact that there was some suspicion that this was an Earth-based thing because they turned up at the same time of day, that ruled out the park's microwave, and it's a great way of doing it. But in terms of where we see them in the, you know, the wider scheme of things, the things that aren't clearly peritons, I don't believe there is any systematic difference between whereabouts the Earth, observed whereabouts the Earth is in its orbit. I think they're completely random, going off across the whole sky. But it's a great question, and it's a great thought, you know, something that you have to be careful of. Are you missing something completely by the fact that it's related to the time of year? As far as I know, these aren't at all, and that would make complete sense.
Fantastic. Well, that brings us to the end of this evening's entertainment.
A bit less entertaining than yesterday, but that's all right.
I would like to just give a quick plug. Let me see if I can make my video work. So finally, Mandu has decided to go to sleep, having clawed my leg for the last 45 minutes. But I would like just to say that we do have some more talks coming up. They're going to go online in the next couple of days. Fred's agreed to talk about dark secrets, the mystery of dark matter, moon mysteries, understanding Earth's nearest neighbour, and planets that never were, unidentified planetary objects. So stay tuned for that. One difference that we are going to make is that we are going to move it to Thursday nights, just so that Fred doesn't have to butt up against the ABC on Wednesday night as well.
But the next one will be on a Wednesday night. That's the
next one is the last of this series, which is medieval astronomy, and we very much look forward to seeing you in 2 weeks' time. We've also got an Ask Fred at 4:30 on Tuesday coming up. So if you'd like to go online and book for that, if you haven't already. But it's really lovely. Fred and I really do enjoy catching up with everyone and seeing everyone's names popping up and all these questions. And Fred, I don't know about you, but I think because people are relaxed and at home, there's more questions. People have got a bit more chance to think about it. Yeah. So, yeah, we will see you in a couple of weeks' time. But thank you very much. And thank you for all the warm comments that are coming through too. Good night, everyone.
Thank you, everybody. Take care. See you next time. Bye-bye.